Okay, section 2 of chapter 2. Ionization of water, weak acids and weak bases. Now we have to keep in mind that when it comes right down to it, water is slightly ionized, okay? Not that it is truly ionized like sodium and chloride, but with any given volume of water, there's going to be a subset of those water molecules that are breaking down. As you see here, equation 2.1. Equation 2.1, water dissociates, hydrogen, free hydroxyl, reassociates, dissociates, reassociates. And this isn't every water molecule. This is only some of those water molecules. And it's not like you have that free hydrogen or that free hydroxyl floating around all the time. Because if you look here at the bottom of this figure, that where they are interacting, the two water molecules to the left are interacting, hydrogen bonding together, the right one will dissociate itself. And going through what they refer to as ionization. It breaks down into two ions. Free hydrogen, free hydroxyl, the hydroxide ion as they refer to it. I keep thinking hydroxyl because I think functional groups. But that free hydrogen is not going to be floating around for long. Because as quick as that ionization occurs, that free hydrogen is then going to link up to a neighboring water and form hydronium, H3O plus. Why is the plus there? Because remember, it's 3 protons in orbit or associated with that one oxygen that only has enough protons for itself. So now it's heavy. So when you go and you look at this, they're associating, they're dissociating. And what's interesting, you start with that hydronium, H3O. Well, that third hydrogen is going to be released rather quickly. It's not permanent. It's going to be taken up, it's going to be released, which is then going to go to the next neighboring water. That neighboring water is going to release, become hydronium itself, releasing one of its 3 hydrogens, going back to H2O. That free proton goes to the next, goes to another one, goes to the next, and the next, and the next. They call this proton hopping. So almost instantaneously, as you see here, this what? 1, 2, 3, 4, 5, 6, 7, 8. 8 water molecules that are all hydrogen bound together. And this isn't all of them that would be hydrogen bound. This is just a sample. You get this proton hopping through the hydrogen bonds. Hydronium gives up a proton, immediately taken up by the neighboring hydrogen-bound water, become hydronium itself, gives up one of the protons, and so on and so on and so on. Near instantaneous, just rushes through. So this building up, breaking down, it's constantly occurring. So we have to have a way to discuss it. AB produce CD, CD goes back to AB, back and forth, back and forth. Well, just that AB here is water, CD here is the free hydrogen, the hydrogen ion, and the hydroxide ion. They come apart, they go back together. They come apart, they go back together in different ways. So, all right. So shown here, you know the equilibrium constant for substrates and products. So let's apply it here. So you look here, equation 2.3 from the chapter. The equilibrium for water is the concentration of the hydrogen ion times the concentration of the hydroxide ion divided by the concentration of water. 25 degrees Celsius. The concentration of water, 1 kilo of water is 55.5 moles. Okay, 55.5 moles of water. So there we go. We've got our denominator. That's the concentration of water. But what's the concentration of hydroxide and hydrogen ions? It's not going to be, the same. So let's figure this out. The production of how much of the water in a given volume becomes ions. This is what's referred to as kW. That's the constant, the ion product of water. We know that the equilibrium, the KEQ of water, is 1.8 times 10 to the negative 16 moles. Okay. So if you go through and you factor all that in, that means the hydrogen ion times the hydroxyl ion concentrations is 10 to the minus 14 molar squared. So that means in any given instant, in 1 kilo of water, there is 55.5 moles of H2O, and in that given volume, 1 times 10 to the negative 7th moles is ionic hydrogen. 1 times 10 to the negative 7th moles is the hydroxide ion. Remember how you do your exponents. 1 times 10 to the negative 7 times 1 times 10 to the negative 7th is 1 times 10 to the negative 14th molar squared. Ah, look. I know what I'm talking about. So at neutral pH, pH is 7, where everything is in balance. Hydrogen concentrations is in balance with the hydroxide concentrations. pH 10 to the negative 7th. Hence we get the pH is a negative inverse logarithmic measure of hydrogen concentration. So negative 10 to the negative 7 mole pH, or negative 7 moles of H, pH of 7. So the pH scale, as I said, logarithmic, negative log of hydrogen ions. So as hydrogen, free hydrogen goes up, pH goes down. As free hydrogen goes up, OHs go down. Keep that in mind. That concentration of H, concentration of O are opposed. One goes up, the other goes down, and back and forth, and back and forth. When they are equal, pH 7, you are neutral. Go one way or the other, more acidic, more alkaline, and so on. You've seen this before, so I'm not going to go beat about it too much, because I just stated it. You go and you look at things that you normally consume. Increasingly acidic means the pH numbers are lower than 7. Gastric juice down there like a 1.5. Lemon juice. Keeping in mind this is a logarithmic scale. It's one of the things students, Gen Chem, in the early bios, they can't seem to quite comprehend. The difference between 2 and 4 isn't just 2 times, it's 100 times. Difference between 5 and 8, not 3 times, it's 1,000 times. Hence the logarithmic scale. How does this apply to us studying biology, studying biochemists? Well, we have to keep in mind that everything we're talking about here in this course, here, in a biology course, we're not talking about things in a test tube. We're talking about things as they would occur in a cell, in a tissue, in an organ, in an organism. So we have to take into account that the range for most of our metabolic reactions is going to be quite narrow. Too high a pH, too low a pH, acidosis, alkalosis. Why is that a big deal? Students ask me that. Why is it a big deal if pH is a little off in, a cell, in your blood? Well, think about it. If you're just discussing enzymes, enzyme function, okay? To have an enzyme, you have to have polypeptides, one or more, quaternary structure. To get the polypeptide to have the correct shape, tertiary structure, you have to have hydrogen bonds, ionic bonds, covalent bonds, hydrogen bonding, and so on and so forth. You want to interfere with ionic bonds, you want to interfere with hydrogen bonds, you want to interfere with even hydrophilic hydrophobic interactions. Change the pH. Those free hydrogens, or the free hydroxide ions, will gum up the works, interfere with those bonds holding the tertiary structure together. Tertiary structure relaxes, change in tertiary, change in quaternary, loss of quaternary shape, loss of enzyme function. What's interesting is, from a chemist's standpoint, as it's applied to biology, hence the biochemistry, we see that certain compounds have distinct characteristics as you go across the pH spectrum, extremely low to extremely high. They call these the acid-base pairs, the conjugate acid-base pairs. That at 1 pH, as the environment changes pH, protons, hydrogen given off, and another, depending upon the compound. Some of them can only give up 1 hydrogen, monoprotic, some give up 2, diprotic, some give up 3, triprotic. You look up at the top here, acetic acid. Acetic acid, around 4.76, calculated 4.7-ish. That's the pKa value for acetic acid. You'll notice that the hydroxyl group will give up its hydrogen. The hydroxyl group of the carboxyl end. Hence you go from acetic acid to ammonia. Or, I'm sorry, acetic acid to that. Ammonia, another monoprotic, up at pKa 9.25, pH 9.25. NH4 becomes NH3. Go down to the diprotic in the triprotic, gives up 2, gives up 3 at different pKa or pH values of the environment. Turns out our bodies are going to utilize this in our cells Turns out, in the different organelles in your cell, the ER, the Golgi, and certain vesicles, pH is not going to be near neutral like everything else. It's going to be more acidic, it's going to be more basic, so that certain compounds, as you see here, become, will give up a proton, will be altered, not through metabolic, not through, enzyme function, just due to change in pH. So as you see, HA, for our acid, under certain points, will give up. You get the free hydrogen ion and the base, A-. And again, there is an equilibrium constant for each of these compounds. So when you look at here again, HA, acetic acid, dissociates, get the free hydrogen ion. Same with ammonium. Same with, and it just keeps going on. Now, I wasn't being facetious when I said, hey, look, the pKa value, 4.72 or pH 7.2, because if you look at the pKa value, it is analogous to the pH. So at this given pH, in whatever set volume that compound happens to be in, there will be a change. There will be a dissociation. When we sit there and we discuss strong acid, weak acid, it's not a discussion of molarity. It's a discussion of how easy, what is the tendency of that compound to give up the proton. If it's quick to give up the proton, thus a lower pKa, thus this is going to occur at a lower pH, we consider it to be a stronger acid. How do we find this stuff out? Well, bane of many chemists. You've probably done this in Gen Chem. I do believe you do it in organic, or have done it in organic. Titration curves. Oh my God, I hated these. These were horrible. Especially if you had to do it all by hand. Ah! Titration curve is nothing more than going through and starting out at pH 1 of a solution with of a solution that has a set solvent and a given solute, and you go through, and as you add in aliquots of sodium hydroxide, base is going to raise the pH. You sit there and you measure the pH after so many set volumes of NaOH, so that as you move up the pH, you start to see, or as you move up the concentration of NaOH, you should start going up pH. You'll see that there's a lag, and then it's going to take off again. That's a titration curve. What you're looking at is the forced dissociation that we talked about a couple of slides ago. At this pH, you're going to see such thing occurring. Loss of a proton here, loss of a hydroxyl there, or something else. So you can go through and you can calculate based on where the curves bend, where you get that lag, where it takes off again. Here's pKa, here's the different dissociation constants. That lag where it starts to bend over, that's the buffering region. That's the region where, as they're showing here, CH3COH, as it increases, it hits a point within that blue box, that buffering region, where the concentration of the COOH and the concentration of the COO, they're in equilibrium. You keep adding more NaOH, pH keeps going up, 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 and then all of a sudden everything goes to the COO. The point where it curves over, the point where it curves up, you take the average between those two, you have the pKa value. And depending upon whether you're dealing with a strong or a weak acid, the titration curve is going to have roughly the same overall shape, but it's just going to be moved up and down the pH spectrum. They're not all going to be down at 4.76. They're going to move up and up and up as you're looking here for ammonium, for phosphate, for acetate. Are the pH curves always going to be so gentle, so, carbon copies of each other? Oh, good Lord, no. But the general idea of how to do them, what you're doing, and what you're getting from them, that's pretty much the same. Just keeping in mind that you're dealing with biological or chemical things that don't always act the same.